Welcome to our first lesson. I want to start off by pointing out that this is a review, and I want to talk about why we're starting off with a review in this class because there's a few different reasons. First and foremost is we want to make sure that you understand what's going to be expected of you coming into this class. And there's certain stuff from the previous class that I expect you to know how to do. So I want to go over all of that, and this is going to be kind of twofold. First and foremost, then, is to make sure that you're in the right class. So if all of this stuff that we go over in this review is foreign to you, you don't remember it, you haven't seen it, or you know that you're not very good at it, then you might not be in the right class. You might want to look at getting into the prerequisite course. So that's the first bit of the review. Now, the second piece is just to review, to make sure that you're bringing you back up to speed. So as you go through this review, expect a little bit of rust. Expect to not remember everything. But what I want you to say is, I remember seeing that before. With a little bit of practice, I can get back to where I was with that. That's what we're hoping to get out of this review. But again, if it's all foreign to you and you don't remember it, then you're not in the right class. So that's kind of why I want to go over this review, is for those two reasons, to make sure that you do review and you remember this stuff, but also if you don't remember it, then you can get in the right class right away. So that's where we're starting with this. With that said, then, I do want to make you aware that this lesson is much bigger than most of our normal lessons. So don't get freaked out, don't get overwhelmed. Just try to do a little bit at a time. I mentioned this during the first class period as well, but I just want to reiterate that this is much bigger because we're covering like 2 chapters worth of material in this review, basically. So anyhow, this is a ton of material, but just try to get through a little bit at a time. If it's stuff that's definitely a review, like you definitely know it already, then you can feel free to kind of speed through. You can turn the YouTube videos up to double speed or something like that if you'd like. So anyhow, getting right into material. The first thing I do want to talk about is a big general theme for the entire course, something to be aware of in algebra. Algebra boils down to basically 2 types of problems: expressions and equations. Expressions are algebraic things that don't have an equal sign in them. So an expression is representing a quantity. So if we don't have an equal sign, we're an expression. Now, one of the things to be aware of when it comes to expressions, then, is that if we start a problem with an expression, then our final answer is also going to be an expression. So usually what we're going to do is simplify them. We're going to simplify them by factoring or multiplying or doing other kinds of things with expressions. But if we start with an expression, we end with an expression. The other big thing that we do in algebra is we deal with equations. Now, equations can be identified because they have an equal sign in them. So if we have an equal sign in our problem, we have an equation. And if we start with an equation, we're going to end with an equation. What we end up with when it comes to equations is something like x equals 5. That's an equation, and that's a solution to an equation because we're trying to figure out what value of x satisfies this equation. So those are a couple big things to keep in mind, and I bring those up because as we go through this review, there's going to be times that we talk about techniques for expressions, like addition, subtraction, multiplication, division. Those are your operations. When I talk about operations in math, the first thing that should clue into your brain is addition, subtraction, multiplication, division. Those are expressions. When we simplify those, we end up with another expression. We are going to deal with equations. We're going to talk about solving linear equations and quadratic equations, both things that you should have seen previously. And we're going to review those. And again, the answer to those are going to be equations. They're going to be x equals something. So make sure that you are always thinking about that every time we see new material in this course. Think about, is this an expression? Is this an equation? What should my answer look like? What is it I'm even doing here in the first place? What type of problem is this? So that's a little intro before we get into our first examples. Now, when it comes to adding polynomials, the basic idea is just going to be to combine like terms. So we're going to start off with 2 different polynomials. They're going to be in parentheses. But the parentheses don't really matter if it's addition. We can basically just remove them, and they got a whole bunch of terms, and just combine like terms. This first example, we can basically ignore the parentheses because the addition sign there is redundant. So we're just going to rewrite this as 2x squared plus 6x minus 5 plus 5x squared minus 10x, at which point all we're doing is looking at combining like terms. So we can identify that when it comes to the x squared, we have 2x squared and 5x squared. That gets us 7x squared. If we move on to the x term, I've got 6x and a minus 10x. That gets me negative 4x. And then as I look at my constant terms, the only constant term I have there is the -5. And so I copy that down. And now that I've combined like terms, that's my answer. So when we're doing the whole subtraction of polynomials thing, really, I want you to take a big step back here. Polynomials are just representing numbers. That's all they are. So when we talk about subtraction of polynomials, it's the same old rules as subtracting numbers. And one of the things you learned early on in algebra is that subtraction isn't really its own operation. Subtraction is just adding the opposite. And that's what you want to think about in terms of this type of problem when we're subtracting, is that we're really just adding the opposite. And the opposite means to multiply by -1. So really, that second parenthesis there, we're just multiplying by -1 is all we're really doing. That's what that negative sign there means. That negative sign there means let's multiply by -1 and distribute that negative across the parenthesis. And once you do that, then it's just combining like terms. Go ahead and do this subtraction. That first parenthesis, again, doesn't really matter. So we can go ahead and just copy everything down directly below it. And one thing I'm going to stress throughout this course is organization. When we work in math, we always work vertically, so we can copy down directly what was above down below. We're not going to do the whole, let's put an equal sign here and then right across. That's not a good idea for organization because that's when you tend to miss things. But also then you start to confuse expressions and equations. This is an expression here. There shouldn't be an equal sign. We're going to work vertically and make sure that we copy everything down just right. And so now we're going to distribute this negative sign across to make this -2x squared, -x, and -5. And then again, just turns into a simple combine like terms problem. I'm going to go ahead and give us a little more room to work. But if we want to stay organized, we can go ahead and say, all right, x cubes. Oh, there's only the one x cubed guy, so let's copy him down. Now we go on to the x squareds. There's a -4 and a -2. That gets me -6x squared. I can move right down the line to the linear term. By linear term, I mean x to the first power. I have 3 minus 1 is +2. And then I get to my constants. I have -7 and -5. Makes -12. And this gets me my final answer to this subtraction problem. Now, I do want to point out real quick as far as my organization of underlining the terms that I've accounted for. This makes it easier to check my work later. I know some people like to organize their work by crossing off terms to say, I already got this. But if you cross something off, it's hard to look back later and check your work and say, hey, did I do all this right? Did I make any mistakes? If we underline them, and if you use color like this, it's not a bad idea to pick up some colored pencils or markers or something. Then we can easily see which ones we are matching up. So just some suggestions there. So let's talk about multiplication. Now, I mentioned previously that when we're talking about polynomials, all the same rules apply as regular old numbers. So I want to take a minute to talk about multiplying regular old numbers, and better yet, to talk about what numbers actually mean the way they're written. So let's actually start there. Let's talk about 532. When I talk about the number 532, I'm saying that I have 5 hundreds. So that's 5 hundreds. I also have 3 tens. That's what the 30 means. So I have 3 tens, and I have 2 ones. So that's what 532 means. And then I'm multiplying by this 41 number. Well, 41 is 4 tens, and it's 1, 1. So we don't write it like this. This would be ridiculous to write it that way. But we have the shorthand that we write 532 to represent 532. And this notation is based on what's called the base 10 system. So when we're talking about 532, this is base 10 because every digit is representing another value whose base is 10. Where the ones digit that we have over here, ones are 10 to the 0. The tens digit is therefore 10 to the firsts, and the hundreds digit is 10 to the second. So that's why we call it base 10, is because we look at each digit, they're representing how many 10 to the zeros, then how many 10 to the first, and then how many 10 to the seconds we have. And so the same thing can be thought of over here of 4 times 10 to the first and 1 times 10 to the 0. Now again, I know this is a really weird way to write this, way too complicated, but there's a reason I'm doing this. I'm trying to make the analogy or make the connection between what we've done previously with numbers and what's going on with polynomials. Because the way that I have this written right now, this looks an awful lot like 5x squared plus 3x plus 2, and this guy looks a lot like 4x plus 1. And so that would be a polynomial multiplication. But let's go back to this arithmetic problem, this 532 times 41. We don't actually write it out like I've written it over there on the right. Instead, the way we write this typically is 532, and then below it we'll do the 41 with the multiplication. And then we'll organize this then by saying let's multiply 1 times each of those. Let's multiply 1 times 2, 1 times 3, and 1 times 5. And then we put a placeholder of 0 down here. And then we're going to multiply the 4 times all 3 of those. So that 4 times 2 gets us 8. 4 times 3 is 12, so we write the 2 and we carry the 1. 4 times 5 is 20. With the 1 that was there, we got 21. Now we add. And we get 21,812. Now, the pattern that we have there is wonderful. Mathematically, what happened is we used the distributive property. That first step of multiplying 1 times everything was I distributed this 1 to all 3 of those. And then multiplying by the 4 was also distribution. I distributed the 4 to each of those, but it was actually 4d, was 4 times 10, and that's why we put the extra 0 at the end, because we actually were multiplying by 40, not by 4. And then once we did that, all of our place values lined up really nice. So the addition part, which is kind of like combining like terms, the addition part was lined up beautifully to have all of our 1s together, all of our 10s together, all of our 100s, all of our 1000s, all of our 10,000s. So it was a nice organized way of handling a multiplication problem. But I point this out because we can really do the same thing when it comes to polynomial multiplication. Example 3, we want to apply that reasoning of organizing our work like we did in grade school in order to make our algebra here, let's scroll off the page there, to make our algebra as easy as possible. We're going to copy down the bigger one up top, and then we'll go ahead and copy the other one below it. And so the first bit of multiplication is to multiply this -1 to all 3 of them. So -1 times -2 is +2. -1 times -3x is +3x. And -1 times x squared is -x squared. Now if we go back to what we did back in grade school, is we then moved on to this 4, and we took him to all 3 of those. Now we did have a placeholder, but here's the beauty of the way that we're doing this. We don't need the placeholder if we just keep track of what we're multiplying. So we would normally put a placeholder of 0 here. 4x times -2 is -8x. And look, he lines up beautifully with the other x person. Now if I multiply 4x times -3x, I get -12x squared. And then 4x times x squared gets me +4x cubed. And now again, as far as the combining of like terms is concerned, everything is lined up beautifully. We have 2 plus 0 is 2. Those are like terms. -8x and 3x, those are like terms. That gets us -5x. -1 x squared and -12x squared gets us -13x squared. and then we copy down the 4x cubed. So again, that same organization that worked well for us in grade school can work well for us here in algebra as well. It organizes your work, it makes sure that you combine all the like terms, and make sure you didn't forget any multiplication. Now, the one tricky thing we do have to be aware of if we're doing this is that we got to make sure that if there's a polynomial that's missing a term, that we account for that in the same way as we accounted for numbers like 202. The number 202, we have a placeholder of 0 there. And so similarly, if I had x squared plus 2, and I was trying to multiply that by, let's say, x plus 1, then we'd want to account for that placeholder by saying I have x squared, I have 0 x's plus 2, and I'm going to multiply that by x plus 1. So that's where you'd want to account for any placeholders if you want to use this organization. I next want to go over a few specific types of multiplication to do reviews on. The first of which is FOIL. FOIL, if you remember, stands for first, outside, inside, last. Again, that's first, outside, inside, last. And I just want to point out that it's not a new way of multiplying, it's not a new technique, it's really just a shortcut. It's just a way to remember which specific things get multiplied together, and it's a very specific instance of multiplying a binomial times a binomial. So a binomial, remember, is a two-term polynomial. So if you have two terms times two terms, this acronym FOIL just reminds you which things to multiply together. You could always organize it in a different way if you prefer. FOIL just one way to organize this. So to use FOIL, we want to go ahead and say I need first, outside, inside, last. We're going to organize our work. And then the F, the first part, says let's multiply together the first term from each polynomial. In this case, that's x times x, which gets us x squared. The O part, which stands for outside, says let's multiply the outside term from each polynomial. So in this case, that's going to be the x's of the outermost one from the left guy, the 3 from the right guy. So 3 times x gets us 3x. We move on to the I part of FOIL. That's the inside or the innermost term. Now don't forget to pay attention to signs. It's not just the numerical value. That anywhere in algebra, if you see a negative, you want to think about that as attached to the next number. So in this case, you don't want to look at that 4 and say that's 4. You want to call that negative 4. So we have a negative 4 times an x. That's going to get us negative 4x. And then the L, remember, stands for last. So the last number from each of these would be the negative 4 and the positive 3. If I multiply negative 4 and positive 3 together, I get negative 12. So there's where FOIL is helping us to remember which things get multiplied together. And again, you could have used vertical method, you could have used distribution. FOIL is just one way to remember what things get multiplied together. Now we still have to finish this out because we then have to say, are there any like terms? And usually the O and the I will be like terms. It's not always the case, but definitely look out for it. So 3x minus 4x gets us negative x, and everything else just copies down. Now back to our organization, I do want to point out here, it's okay to leave some space in your answer. You don't need to cram together everything. So I left this spread out so I could easily copy down from one step to the next. My x squared copied straight down. My negative 12 copied straight down. The negative x, it's clear it came from the 3x minus 4x because it's right in between them. So it's a way of staying organized. We always want to think about staying organized because I don't believe there's such thing as silly errors. So some people call some errors silly or careless errors. Well, if you have a careless error, show more care in your work. If you have a silly error, don't be silly when you're doing your math. So let's come up with a good way to organize our work so that those errors don't happen. And when they do, we can easily find them. And that way we don't actually report an error. So we always want to think about how to check our answers and how to make sure that our answers are correct. All right, so let's talk about our next special case. This one comes up a ton when we square a binomial. So I have on here a plus b squared, but this is just to represent any binomial, two terms that we have, and we're multiplying by itself. Now, what you probably have done in the past is you probably went ahead and just FOILed this out. So in the past, you probably rewrote this as a plus b times a plus b. And that's perfectly fine. You will get the right answer. But the reason I want to take some time to go over this is because this is something we're going to do so frequently in this course that you're going to want to make sure you know how to use the formula that's associated with it. Because there actually is a formula. And with that formula, we want to be able to apply that formula in order to kind of speed things up. And that's always the idea of a formula. A formula is just a way to combine a whole bunch of steps into one step. So if you were to FOIL this out, then we could do first outside, inside, last again, where first is a times a, which gets us a squared. We could then go with outside. Outside would be a times b. So that's our O, is an AB. And then if we went with the I, well, that's also AB. You know, it's BA, but who cares about order of multiplication? So we'll call that AB as well. And then our last is b times b, or b squared. Now, just like always with FOILs, our two middle terms, we're going to see if we can combine like terms. And I have 1ab plus another 1ab. So that gets me 2 ABs. And so that gets us the formula in question. So I wanted to go through those steps for a couple reasons. One is to point out that this formula that I have highlighted in yellow here, that's not some magic formula that I pulled out of thin air. It's math. If you square a plus b, so if you do a plus b times a plus b, you're going to get a squared plus 2ab plus b squared every single time. And so this is something that if instead of memorizing it, you want to come up with it, you definitely could. But we're going to go over in the next examples how to actually apply it, and that's the important thing. Because as I said, this is going to come up a lot in this course. It's going to come up in very tricky situations where it's going to end up being easier to use this formula than to FOIL things out. But the whole idea with that is that we got to get practice now. You got to get practice using it right now so you know how to use it with easier problems. And some of these easier problems may actually be easier to FOIL. But you need the practice. You need the practice using this formula. So as you read this formula, instead of reading it as a whole bunch of letters, what I want you to see is I want you to notice that you're squaring the first thing. That's what the a squared means. Whatever the first thing was in the original binomial, square it. For this middle term of 2ab, I want you to see that as multiplying the two things together that you originally had in the binomial. That's the a times b. Multiply them together, and then double it. That's what the times 2 means, is multiply the first two things together, the a and the b, and then times by 2, double them. And the last term is just your b squared, so it's the second thing in the binomial squared. So now we're going to apply that reasoning to this problem here. So I'm going to jot down the formula one more time, that when we have a plus b squared, that's going to give us a squared plus 2ab plus b squared. And I had mentioned before that we really want to think about these as the first thing squared, the middle thing there, that's the product of our two values times 2, and then b squared. So in our example here, our a value is 2x. Our b value is negative 3, because again, when there's a negative sign in a problem, that's just attached to the number after it. So when we go to our a squared area, that's our first term squared. If we take 2x and square it, that gets us 4x squared. For our middle area, if we take our two terms and multiply them together, so 2x times negative 3 is negative 6x. And then we're going to double that. So if we double that, we get negative 12x. And for our b squared, we take negative 3 and we square it, and that's going to get us 9. So overall, we're getting 4x squared minus 12x plus 9, and that's how we multiply this out. And again, this might seem easier to FOIL it out in just combine like terms, but please trust me. I know it's coming up in the course. It's going to end up being easier if you start to get used to this formula here, so you can start to figure out how to square binomials. When we start to introduce radicals into the mix, other complicated things into the mix like logarithms, it's going to be easier to know how to apply this formula. And also when we're factoring, we're going to be able to go backwards. If we can identify when we see a perfect square like this, we can factor it back into a perfect square. So that's why I want to get a little practice right now with using this formula. Now the next thing I want to talk about is going to be division. Now division is also not its own operation really in math. That division is just multiplication by the reciprocal. So that's what we're going to keep in mind as we look at the very specific instance of dividing a polynomial by a monomial. And remember with these terms, monomial means a single term. So if we have a single term in the bottom of a division problem, then we can think about this as multiplication by the reciprocal. So our top is going to be in parentheses, and we're going to multiply by 1 over the bottom. So if we have a top that's in parentheses and we're multiplying by something, then really what's going to be going on is we're going to distribute this. So we can turn that into a distribution problem. It's going to go into every single term. So this is kind of how we want to picture what's going on when we're doing division. Let's a lot of times think about it like it's really a multiplication by the reciprocal problem. Look at an example of what I mean. So this is an example where up top we have a polynomial, and in the bottom we have a monomial. Again, monomial means there's one term. So what we can kind of think about is going on here is we can think about this as 6x to the 5th plus 9x to the 4th minus 3x. We can think about that as being in parentheses, and then it's multiplication by 1 over 3x squared. So that really means the same thing, that to divide by 3x squared means the same thing as to multiply by 1 over 3x squared. What happens then when I distribute this is as I distribute to the first term, it becomes 6x to the 5th over 3x squared. For the second term, it's 9x to the 4th over 3x squared. And for this last one, we're going to end up with a 3x in the top and a 3x squared in the bottom. So if you look back to the original problem, we really could have jumped right to this step without that intermediate step, but I wanted to point out why we can. So this is why we can distribute when it comes to division, is because we can think about division as multiplication by the reciprocal. Now with each of these terms, we can now simplify them. With that first term, 6 divided by 3 is 2. And if I have 5x's on the top and 2 on the bottom, we subtract. 5 minus 2 is 3. So 2 of them divided out. For the second term, 9 divided by 3 is 3. X to the 4th over x squared leaves me an x squared. Now we got to be careful. Now the subtraction sign carries down. We can think about it again as a negative sign if we prefer. The 3's divide out. Remember, dividing out means they're equal to 1. That 3 over 3 is 1. So similarly with our x over x squared, we want to think about that as x over x times x. The x's will divide out, leaving an x in the bottom. But by dividing out, we mean we're left with a 1. Because anything over itself is 1. So that simplifies down to 1 over x in that case. And there's our answer to the division problem. All right, so let's talk about dividing polynomials that aren't simply dividing by a monomial. Well, let's take a step back. Let's again talk about how this works with numbers. So that's what we're going to do first, is we're going to talk about how we can handle division with numbers. And this is going to come about from long division. So we're going to do a quick review of long division. So if we divide 197 by 16, we rewrite this with the 16 on the outside and the 197 down below. Our first step of doing this division is to say, how many times does 16 go into just the 19 there? So we're not going to look at the whole number, we're just going to look at 19 and say 16 goes into 19 once. And we're going to go ahead and put that 1 directly above the 19. And so that's our first step, is just to get a rough idea of where to start, to say, all right, that goes in that many times. Then on the outside, we're going to multiply those two numbers together. So we're going to multiply 1 and 16 to get 16, and then subtract. 19 minus 16 is 3. Okay. So once we have that, we basically are going to start over. We're going to say, I got this 3 left here. Drop the 7 down, and we have 37. And we're going to start over. We're going to say, how many times does 16 go into 37? So 16 goes into 37 twice. And then, well, again, we're going to go through the same things. 2 times 16 is 32. We're going to subtract this and get 5. Now, there's a couple things that can happen now. We can go ahead and just say remainder 5, or you can remember what that remainder means. So we're dividing 16 into this, and we have 5 left over. That means we have 5/16 left over, and that's really what the remainder of 5 means. So our answer is that it goes in 12 times, but we have 5/16 left. An example of a division problem. And in this situation, we will be using long division of polynomials because of the fact that what we're dividing by has more than one term. So what we're dividing by over here has 2 terms. It's the x plus 1. So we want to start off by rewriting this as long division. Put the x plus 1 on the outside, and on the inside we can get the 5x squared minus 14x minus 3. Now our first step here is to say, how many times does x go into 5x squared? The beauty here is we can ignore the plus 1. We're just caring about the biggest power, the biggest term in each of those. And so really what's going on in our heads is we should be thinking 5x squared over x is 5x. Now the next step in long division is the multiply. We want to multiply the 5x that's up top times the x plus 1. And so we literally do want to distribute here, and that's going to get us 5x squared plus 5x. The next step when it comes to long division is our subtraction step. Oops, I erased part. We're subtracting, and here's the important part, we're subtracting that entire polynomial there, that entire 5x squared plus 5x. So by putting parentheses there, I remind myself I'm subtracting the whole thing, and that means to distribute that negative to both of them. That way when I do the subtraction, 5x squared minus 5x squared is 0, but now negative 14x and negative 5x makes negative 19x. Now we'll go ahead and carry the negative 3 down, and that's one full step of long division of polynomials. The next thing to do is to basically start over and do it all over again. And so again, we'll say, how many times does x go into negative 19x? And that's where we're going to think, all right, negative 19x over x, the x's divide out, and I'm left with negative 19. Now is where we multiply. We're going to multiply that negative 19 times the x plus 1. And that's going to give me negative 19x minus 19. Now with that, now we move on to our subtraction step. But again, we're subtracting that entire thing. So we put parentheses around it. I distribute that negative to both terms, and 19 minus 3 is just 16. And that 16 is my remainder. I'm going to write that by adding 16 over x plus 1. Now, just a little suggestion, do not forget the plus right there. That's where I see a lot of people make mistakes, is they're so focused on what the remainder is, they write it right next to it. But this is an addition. We have an answer of 5x minus 19, plus we have a remainder, so we do need to have that addition. Let's go ahead and change gears. Now we're going to talk about factoring. So factoring is a super important part in algebra. We're going to use it in almost every single chapter. So we're going to do an extensive review here. And that way, again, in case some of this is a little bit, in case you're a little rusty in it, you can shake that rust off and get some practice. But if this is stuff that you're not familiar with, then it's really important that you take the prerequisite course so you can get a good, firm foundation in factoring. Now, the whole idea of factoring is, of course, that we want to unmultiply. We're trying to figure out what things are multiplied together to equal this original expression. Now, we're going to talk about strategies and what to do in order to factor, but the number one important thing to do is every single factoring problem, no matter what it is, your very first step is always the same. Your first step is always to factor the greatest common factor. And so we're going to look at other strategies in a minute, but no matter what, your first thing to do is to factor the greatest common factor. And so that's the first thing that I want to talk about, is in doing so, in how to factor out the greatest common factor. The whole idea of factoring out the greatest common factor is basically to undistribute. So in your notes, you have the distributive property written out. And what we're going to do is we're actually going to work right to left. We're going to say if I start off with AB times AC, if I notice that both terms have an A in them, then I can pull that A out front. And that's the whole idea of factoring, is to say, what do I have in common between both of these terms, or in some case between three terms, to say what factors in common between all of them. Now, if we want to look big picture on factoring, once we're done with this first step of factoring out the greatest common factor, the next thing we do is we actually count how many terms there are. And that's where we're going to go beyond this in the lessons. We're going to say, well, what do we do if we only have 2 terms in our polynomial? How do we factor that? Or if we have 4 terms, what do we do then? What if we have 3 terms? And we're going to do something different depending on how many terms we have. But we're first of all going to try to factor out the greatest common factor. Then we're going to look at the number of terms, and we're going to look at strategies based on how many terms you have. So let's look at this example on factoring out a greatest common factor. What I want to do with this 6x squared plus 9x, well, it's not that hard to do in and of itself, is I want to try to rewrite this in a way that's a little bit closer to the whole distributive property idea, just so you can see exactly what's going on. So 6x squared, if I want to say, well, what are the factors of 6x squared? 6 comes from 3 times 2, and x squared comes from x times x. And yes, I wrote these in a weird order, but on purpose. 9 comes from 3 times 3, and we have an x. So this whole thing I have underlined is one term. This is 3 times x times 2 times x. So we can think about a little multiplication sign in between each of those. And then 3 times x times 3 is also one term. So what this should kind of look like to us is it should kind of look like what we have in our notes as AB plus AC. Where the A in this case, the part that's in common, is both of these things have a 3x. And so that's the common factor that I can pull out. And in pulling it out, I can say, well, what's left? From the first term, after I pull the 3x out, I'm left with a 2x. And from the second term, when I pull the 3x out and see what's left, I'm left with a positive 3. And the beautiful thing about factoring, and especially factoring greatest common factor here, is that we can always check our answers by multiplying it back out to see if we get back to the original problem. So in this case, if you were to distribute the 3x across, you better get back to the original problem, because this is an expression where our whole goal here is just to rewrite it. Our final answer should be equivalent to the original problem for every value of x. And so if we distribute it back through, it should be equal. So if we look at the second example, One trick I want to talk about when it comes to problems that have numbers and multiple letters here is to start off and just say, let's break this into three separate problems. Let's look at the numbers. What do 24 and 6 have in common? Well, they both have a factor of 6. And then I want to look at the a's. The first term has an a, it's got a to the first, and the second term has an a, it has a to the first. So they have an a in common as well. And then if I look at the b's, the first term has two b's, it's got b squared, so that's b times b. The second one only has one b, so they both have at least one b. So that's my greatest common factor, is the 6ab. Now to see what's left, if I had 24ab squared, and I factored out or divided out 6ab, 24 divided by 6 is 4. The a's are kind of gone though. There was an a there originally, I pulled it out. Now there were two b's there originally, and I pulled one of them out, so there's still a b there. Now it comes to the negative 6ab, and I pull out 6ab from that. If I pull a 6 out, there's nothing left. But what do I mean by nothing? If literally I'm dividing this out, 6 divided by 6 is 1. If I pull an a out, then that's gone too. And I pulled the only b out that was there. So I pulled everything out. But really in dividing this, I'm dividing something by itself. I'm really left with a 1. And this 1 we can verify then again that if I were to distribute it back out, without that 1 there, I'm not even going to get a second term. So it should make sense that if we're factoring out a greatest common factor, if our original problem had two terms in it, we better have two terms in the end too. Otherwise we can't get back to the original problem. So there's our properly factored form for factoring out the greatest common factor. Now, once we're done factoring out a greatest common factor, the next thing we're supposed to do is look for the number of terms. And so when we have two terms in our polynomial, we're always going to do the same thing. We're always going to apply one of the special formulas. And that's what we're going to go over now in this lesson, is we're going to go over what those three formulas are. And if none of the three formulas apply, and you can't factor out a greatest common factor, then your polynomial is what we call prime. Just like a prime number is a number that doesn't have factors besides one itself, if a polynomial can't be factored, we call it prime. So when we have two terms, we try to apply the formulas. And the first formula we're going to talk about is the difference of squares formula. And so when the binomial has terms that are squared, so when we see x squareds in them or we see numbers that are squared like 25, that's a good indication that difference of squares is going to apply. Now, the other important thing, of course, is that the sign between those two terms is a subtraction sign, is a difference. That's when we use the difference of squares formula. And that difference of squares formula tells us if you have a squared minus b squared, if you have a difference of squares, then you factor it as a plus b times a minus b. And that's always how we'll factor. Now note that there is no such thing as a sum of squares formula, that if you see a squared plus b squared, that can't be factored. Look at an example of factoring using this difference of squares formula. And so again, the first thing to do is identify that the difference of squares actually applies. And that comes from the fact that we have an a squared minus b squared situation, that the first thing we see, the 9x squared, is in fact a square. 9 is a perfect square, it's 3 squared. 4 is a perfect square, x squared, y squared, all squares, all beautiful things. And so we know that we are going to factor this as a plus b times a minus b. So we just got to say, all right, what's the a, what's the b? And that's something that I would do if I were you in terms of organization, is literally writing that down to say, what is my a, what is my b? My a is to say, what is it that I'm squaring to get 9x squared? And that would be 3x. And my b would be to say, what is it I'm squaring to get 4y squared? And that's 2y. And that way when I factor this guy, I'm factoring him as 3x plus 2y, because that's my a plus my b, and then 3x minus 2y, because that's my a minus my b. And that's the proper factorization for this problem. Talk about the next two formulas. So we already talked about the difference of squares, and we said there is no sum of squares. So let's talk about cubes. There is a difference of cubes and a sum of cubes formula. So if our binomial has terms that are cubes, so if we see x cubed or y cubed, or we see numbers that are cubes, like 1 or 8 or 27, then that's an indication that it might be one of these formulas of sum of cubes or difference of cubes. So if those terms are cubed and the sign between the two terms is a subtraction sign, then you probably have a difference of cubes. If you have a binomial that's got terms that are cubed and the sign between them is a plus, then that's going to be the sum of cubes. So that's kind of how we're going to identify which of these is which. Now I want to have these up at the same time so you can see the similarities and differences between them. So one thing that I want to point out that's going to hopefully help you memorize these, because you should memorize these formulas, is I want you to notice that the sum of cubes starts off with subtraction. I'm sorry, I said the wrong thing there. The difference of cubes, sorry, starts off with subtraction. The sum of cubes starts off with addition. So if you have a cubed minus b cubed, the formula starts off a minus b. When you have the sum of cubes, if it's a cubed plus b cubed, the formula starts off a plus b. Now in both cases, then, the next sign that we see is opposite. So I want you to notice that that second sign, the one by the AB, is opposite of whatever we had to begin with. So when we had a minus b, the next sign is plus. When we had a plus b, the next sign is minus. And then lastly, I want to point out that when it comes to the b squared is always positive. Now you can remember this by saying squaring something always results in a positive. So this can hopefully help you memorize the formulas because, again, you should have these formulas memorized. So let's go ahead and try to factor this polynomial here. So again, we start off with greatest common factor and say, is there a factor that's common between them? Now 27 is 3 times 3 times 3, so it's just a bunch of 3's. And 8 is 2 times 2 times 2, so there's a whole bunch of 2's. Nothing in common between them, but again, greatest common factor should always be our first step. Since there's no greatest common factor, the next thing we do is count the number of terms. Because we have two terms, one of our special formulas apply. Now in this case, we do have some cubes going on, and there's subtraction between them. And so we figure that most likely what's going on here is that we have an a cubed minus b cubed situation. Now what I would do if I were you is every time write the formula out. This is going to help you because then you can just go ahead and copy directly below that what you want to plug in. So we're going to say, what is the a? What is the b? So what is it that I'm cubing to get 27x cubed? And that's 3x. I'm cubing 3 to get 27. I'm cubing x to get x cubed. Similarly for the b, what am I cubing to get 8y cubed? I'm getting 2y. 2 cubed is 8, y cubed is y. And once I identify that, now it's just a matter of plugging into the formula. A is 3x. B is 2y. I'm just copying directly down below, a minus b. Now when I square the a, I'm squaring 3x. Think about that 3x as being in parentheses. 3x times 3x is 9x squared. Now when I multiply a times b, I'm multiplying 3x and 2y together. 3 times 2 is 6, and then I get xy. When I square the b, I'm squaring 2y. That gets me 4y squared. But there's my answer. I write the formula out, I figure out what's the a and what's the b, and I plug them in. And that's how we factor using a difference of cubes. Factor this one. Again, first step, greatest common factor. Always start there. Now, we try to do the greatest common factor whenever possible, but when you're dealing with big numbers like this, sometimes it might be helpful to start off with just some common factor. So in this case, you might notice, hey, both those numbers are even. Let's at least start there. Let's factor a 2 out and see what's left. That leaves me with 125 x cubed and 27 y cubed. And then you can always just say, hey, can I do better? Well, 125 is 5 times 5 times 5, and 27 is 3 times 3 times 3. So no, I don't think I can do better. I think that's as good as I can get. Well, now we got to look at that binomial and say, can I factor him using a special formula? And sure enough, I do have an a cubed plus b cubed situation. Now keep in mind, we factored this 2 out, and he's got to stay there. So when I look at my factoring formula for a cubed plus b cubed, and I write it down as a plus b times a squared minus ab plus b squared, I got to keep in mind there's a 2 out front there. No matter what, that 2's got to stay there. I factored him out. He's not going away. He's staying there. But now we got to identify what is the a and what is the b. So if I look at the a, what is it I cubed to get 125? That's 5. And of course, an x to get the x cubed. And for the b, I cubed 3 to get 27. I cubed y to get y cubed. Now I got my values to plug in. Let's plug them in. The 2 copies down. The 5x and the 3y copy down. Now as far as the a squared is concerned, I'm squaring 5x. That's going to give me 25x squared. As far as the ab, I've got 5x times 3y. That's going to give me 15xy. And as far as my b squared, I'm taking 3y and squaring it. That gets me 9y squared. Now, even though that last parenthesis looks like maybe he could be factored further, don't even worry about it. We'll discover later in the course why it's not going to factor any further, but just go ahead and leave it be. So we talked about factoring out greatest common factor as your first step. We then said count the number of terms, and if you have 2 terms, then you're going to use a special formula of either difference of squares or sum of cubes or difference of cubes, and there is no sum of squares. So the next thing I want to talk about is 4 terms. When you see 4 terms in a polynomial, we always do the same thing. We're going to do factor by grouping. We're going to group 2 of them together and the other 2 together, and then we're going to use greatest common factor within each of the 2 groups. Now, if you have 4 terms, and you group them together in some way where factor by grouping doesn't work, try to rearrange the terms and do it again. Try to group them in a different way. So instead of grouping the first and second together and the third and fourth together, maybe rearrange them and look at the first and third with the second and the fourth and see how that works out for you. So let's go ahead and look at an example of that. All right, so let's do some factor by grouping here. We've got these 4 terms, which is how we identify that this should be factor by grouping. And we're going to group together these terms here and these terms here. Now note this is not a multiplication problem, that realistically there's still an addition sign between these. We didn't change the operation just by putting parentheses in there. But we're just grouping together the first 2 and the last 2. And with the first 2, we're going to pull out a greatest common factor. We're going to say, what's in common between 2xy and 10x? And so clearly there's a 2 in common between them. They also both have an x. When I factor that out, I'm left with a y. And from the second term, I'm left with a 5. Now, from the second term, I've got negative y and negative 5. And I want to look at those guys and say, what can I factor out of a negative y and a negative 5? Now, on first glance, they don't have anything in common, but we can always pull out a 1 or else pull out a negative 1. And it's our decision on which one to do, but basically what we want to have happen is we want to have the parenthesis that's left over, we want those to be matching between the 2 things that we group together. So I'm going to factor a negative 1 out.
and that would leave me positive y and positive 5. Now here's where things get confusing, so I actually want to look at a completely separate problem that's a whole lot easier. I want to look at the problem 2x times a minus 1 times a. And I want to try to factor this. And that's much easier to factor. In that one, we can use the GCF, the greatest common factor, to say, hey, they both have an a in them. The first term, I'd be left with a 2x. The second term, I'd be left with negative 1. That's easy. That's a piece of cake. But then I want you to realize that that's really all that's going on over here in our actual problem. Only instead of an a, I have a y plus 5. So I want you to notice that our entire first term there has a factor of 2, x, and y plus 5. Our entire second term there has a negative 1 and a y plus 5. Both terms have a y plus 5 in them. So we're going to bring that y plus 5 out in front, just like we brought the a out in front in the simple problem. Now once I've factored a y plus 5 out of this first term, what's left? Just the 2x. When I factor the y plus 5 out of the second term, what's left? Just the negative 1. And so that's how we factor by grouping. Let's continue our discussion of factoring. So we've already said that we're going to start off by factoring out a greatest common factor first and then count the number of terms. When there was 2 terms, we used one of the special formulas, difference of squares, difference of cubes, sum of cubes. When there's 4 terms, that's when we did factor by grouping. And now we're going to talk about 3 terms. Now when it comes to 3 terms, I'm going to start off talking about, in general, how we handle factoring with 3 terms. Now we are going to look at a few special cases where things might be a little bit easier in the special cases. But what I talk about in general here will always work. So what I want to talk about is I want to talk about an educated guess, check, and revise method. So I do want to point out this isn't just simply guess, check, and revise. We're going to make smart guesses. If we just did guess, check, and revise, we could be there for a long time with a ton of guesses. So what we're going to do for our educated guess, check, and revise is we're going to set up some parentheses and we're going to figure out what could possibly go in there to be a smart guess. Now this guess might be right, it might be wrong. We're going to check it and say, is this the right way to factor? If it is, we're done, we're good. If it's not correct, then we'll go ahead and start over. So the way we're going to make this smart guess is we're going to make sure that no matter what, the f and the l portion of FOIL are correct. So we're going to say if I multiply the first 2 things together, that will get me my squared term that I know I want. If I multiply the last 2 things together, I will get the constant term that I'm trying to get. So we're going to guarantee those 2 to be correct in the guess portion. Now, as far as FOIL is concerned, we also have to worry about the O and the I. So we're going to check that. That's going to be our check, is to say, if I multiply this out, do I get the correct O and the I? If I do, then my F is correct, my L is correct by default because I made it that way. The O and the I are correct because I checked them, so I must be correct. We're good. But if the O and the I are not correct, that's when we're going to revise. We're going to start over. We're going to go back to that step that we guessed at making sure the F and L are correct, and we're going to pick a different combination. And so that's how we're going to go about this guess, check, and revise method. Now, as far as being educated guess, the one extra caveat that I want to talk about is to say if our original problem does not have a greatest common factor, then none of our individual factors better have a GCF. So we're not going to make a guess at, let's say, 4x plus 2 if I didn't have a greatest common factor in the beginning. Because 4x plus 2 has a greatest common factor of 2. So I don't want to use that as a guess if the original problem didn't have a greatest common factor to begin with. That wouldn't make sense. That'd be a bad guess, so why even bother doing it? So let's go ahead and try this whole guess, check, and revise business. So let's try a guess, check, and revise on this first example of 20x squared plus 23x plus 6. So remember, the educated guess portion is to start off by guessing that the f and the l are correct. So by the f, I want to find things that multiply to be 20x squared. So maybe I'll try 10x and 2x. Then I need to guess to make sure the L is correct. So I need to find things that multiply to get me positive 6. So maybe 3 and 2. But here's where that educated part comes in. This would be a bad guess that I wouldn't even make. Because of the fact that there's a greatest common factor of 2 that I could pull out front. But if I look back to the original problem didn't have a 2 I could pull out of everything because my middle term was odd. So this would be a bad guess. And so maybe instead of that guess, maybe I would put the 2 first and the 3 second. Oh, but then all of a sudden I've got a greatest common factor there. And you know what? 10 and 2 don't work because since they're both even, I need to pair an even number in with the L portion. So as far as the educated guess, check, and revise portion is concerned, 10 and 2 is not a very good educated guess. Let me instead try 5x and 4x. That will also get me 20x squared. So now for my 6, where I want to use 3 and 2, I know not to put the 2 over here because again, I'd have a greatest common factor. And I know that I shouldn't have a greatest common factor. So instead, maybe I put the 2 here and the 3 here. So there's our educated guess. There's a reasonable guess. I don't know if it's right yet. It might be wrong. To check this, I check it using the O and the I from FOIL. The O, remember, is the outside, where I take 5x times 3 and get 15x. The I is the 2 times the 4x, which is 8x. That gets me 23x, which is indeed what I was trying to get. So that tells me that I have a good guess here. My good guess must be correct, and this is the correct answer. So let's go ahead and look at the other one. This one's a little bit harder in some ways, because there's lots of different signs going on here. Now, as far as the first part of my guess, is pretty simple. I only have the one option, 5x and x. That guarantees the f portion of FOIL is correct. Now I need to guarantee that the L portion of FOIL is correct. I need to multiply to be -3. So maybe I'll try +1 and -3. That multiplies to be -3. That's a reasonable guess. I've guaranteed the f is correct by 5x times x is 5x squared. I've guaranteed the L is correct. 1 times -3 is -3. Now I need to check, let me actually do this a little bit higher up there. I need to check that my O plus I is correct. That's the check part. My O is -15x. My I is 1x. This gets me -14x. That's not what I was trying to get. I was trying to get -2x. This is not a correct guess. So now I revise. Now I'm not going to cross this off. I'm not going to erase. I want to leave my good guesses there so I remember what it is I've already guessed at. I'm just going to try again. I like my 5x and my x, but instead of +1 and -3, maybe I need to flip-flop those two. Maybe I need to put the -3 there and the +1 there. That's going to get me 5x for the O and -3x for the I. That gets me +2x. Well, I'm getting there. I wanted -2x. I got +2x. The beauty here, though, if all that's messed up is the sign, then you know how to revise. We revise by flip-flopping the signs. So instead of -3, let's make that +3. Instead of +1, let's make it -1. Now my O is -5x, my I is +3x. That gets me the -2x that I wanted. Now I'm happy. Now I've factored correctly. And so that shows the revision steps, how we revise. Now we're going to look at a very special case of a 3-term polynomial and trying to factor it. And that special case is when your lead coefficient's 1. Now, we're basically going to do the same thing with the educated guess, check, and revise. But the guess part is so much easier now that we can kind of do the check in our head and not need to revise as much. So let me go ahead and remind you where this all comes from so you can kind of do this on your own. What we're going to do is actually work backwards first. So this isn't solving a problem. This is just sort of explaining where it's coming from so we can see why we do what we do. So let's go ahead and just multiply this out and see how this works out if I multiply those two polynomials together. So we're going to FOIL it out. So we're going to do FOIL, where our F is going to come from x times x. That's going to get us x squared. Our O, our outside, is -2 times x. Our I, our inside, is 3 times x. And our last is 3 times -2, which is -6. And then if we do our combined like terms, we get x squared plus x minus 6. So that's all well and good, but now let's get to the actual factoring part. What if I asked you to factor that? So if I asked you to factor x squared plus x minus 6, the goal of that, to factor it, is to say what two things multiplied together equal it. Now, of course, in this case, we already have the answer to that, but I want to point out where this stuff came from. Because if we start off saying, all right, where'd this guy come from, this x squared? Well, he came from the f. So that means we would guess at x times x. And that's where I was saying earlier that the guess part is easier because if our lead coefficient's 1, if we just have an x squared, it's always x and x. So then the next part of the guess would normally be to say, let's make sure that L is correct. So we would want to make sure that whatever goes in those blanks there multiply to get us -6. But if we look at where did that plus 1x come from, that plus 1x came from the O plus I. Well, that was -2 and +3. And so really, we want to make sure that we add to get your middle coefficient. And so really, that's all it takes to factor a trinomial, factor a 3-term polynomial whose lead coefficient's 1, is to say, I need to multiply to equal that last number, and I need to add to equal the middle coefficient, and then I can just set it up as that parenthesis times the parenthesis. So let's look at an example so we can see that in action. So if we're looking at the example x squared plus 5x plus 6, and we try to use the same reasoning, then we need something that multiplies to get us +6, but adds to get us +5. And once we figure those numbers out, we're going to put them into x plus 1, x plus the other, and that's it. And so if I want to find two numbers that multiply to be 6 but add to be 5, it sounds like 2 and 3 would probably work. I put them in there, and that's it. There's my guess, check, and my revise all together in one, because I'm guaranteeing the L is correct by making sure that they multiply to get me 6, and I'm making sure that my check part, the O plus I, works out, because I'm making sure that they add together to equal the 5x. And so really this is the guess, check, and revise method. It's just all together in kind of one step to say, I would normally guess to make sure that I multiply to get 6, and I'd figure something out to make sure they add together to equal the 5. But now we're just going to say, all right, do it all in one step. So for the second part of this example, on this one we're looking to say, I want to multiply to equal positive 20, but add together to equal negative 9. Now the fact that I'm multiplying together to equal a positive number tells me either both my numbers are positive or else both of them are negative. Because if I'm multiplying something times something and getting a positive, they're either both positive or both negative. Now if I'm adding together to equal a negative, they both must be negative. So we kind of know a little bit about the signs ahead of time. That's going to be x minus and x minus. And so numbers that multiply to be 20 and add to be 9 would be 4 and 5. And so that's our correct factorization. So we've been talking about using educated guess, check, and revise to factor three-term polynomials, trinomials. Now there is another strategy that we can use called AC grouping. Some people like this, some people don't, so I'm just throwing out there's a possibility. The basic game plan of this method is to take your three-term polynomial and rewrite it in a very special way, but to rewrite it as a four-term polynomial. And once you rewrite it as a four-term polynomial, then you can use factor by grouping. So if you really liked factor by grouping, this might be a method that you like. Now this can also be handy when there's a lot of things to guess at. This method takes about the same amount of time no matter what, whether or not you kind of guess in the first guess or guess 10 guesses down the line. There's no guessing involved in this method, so it takes about the same amount of time. Whereas guess, check, and revise, sometimes you guess right away and it's quick. Sometimes you have a whole bunch of revisions and it takes you a long time. So that's the nice thing about AC grouping is it takes you about a middle amount of time every time. So anyhow, we're going to go through the steps here. The first step is to multiply the a and the c together, and by that I mean the first coefficient, so the coefficient of the x squared, and the constant term. We're going to multiply those together, and this number is just going to help us to figure out how to break this thing down. We're then going to take that big number of a times c, whatever that is, and we're going to look at all the pairs of factors, two things that multiply together to equal ac. And once we have that list of pairs, we're going to figure out which of those add up to be your middle coefficient. We're going to use that pair then to rewrite the middle term, and in doing so, that's when we have a four-term polynomial. And once we have that four-term polynomial, we can factor by grouping and get ourselves an answer. So that's the basic process. Let's go ahead and look at an example. Do those steps with this example. Our first step is to multiply the a and c together. So if I multiply 20 and 6 together, I get 120. Now with that number 120, I'm then supposed to list out all the pairs of factors. So 1 times 120, 2 times 60, 3 times 40, 4 times 30, 5 times 24, 6 times 20, 7 doesn't work, 8 times 15, and 10 times 12. Now we don't need to keep going because if you notice the pattern that I'm going with, the next thing I'd see for my first number that would work would be 12. That would give us 12 times 10, and we've already accounted for that pair. So our next step after we have all these pairs of factors is to find the pair that adds up to 23. So that's 8 and 15. Next step is to rewrite our middle term. So this is all kind of scrap work that we've been doing. Coming back to our problem now, we're going to rewrite this problem. Instead of 23x, we're going to write it as 8x plus 15x. That's the only thing we're changing about the problem is instead of 23x, we now have 8x plus 15x. Nothing changed, that's equivalent, but now we have four terms. And now that we have four terms, we can factor by grouping the first two and the last two together. From the first two, we can pull out a 4x. That leaves us 5x plus 2. From the second group, we can pull out a 3. That also leaves us 5x plus 2. And now we can pull the 5x plus 2 out, leaving a 4x from the first term and a 3 from the second term. And that's how we can use AC grouping to factor a trinomial. Now we're going to shift gears to talk about equation solving. In your previous math courses, you should have seen two different types of equation solving, linear equations and quadratic equations. You probably also saw some rational equations. We're going to review those later. We're going to touch on linear equations first. And so just to make sure that we're on the same page as far as how that's defined, a linear equation is any equation that can be written in the form ax plus b equals c, where a isn't 0. So in other words, there's an x in the equation somewhere, and that x is only raised to the first power. A solution to an equation is going to be the x value or values that make the equation true. That when we plug it in, it becomes a true statement. That's what we're looking for in solving any equation, no matter what it is. Now, the basic steps we're going to go through in solving a linear equation is we're going to start off cleaning it up, get it into a nice form, because linear equations can come in lots of different forms. And so we're going to maybe use the distributive property. If there's parentheses, so we can get rid of our parentheses. If there's fractions, we're going to get rid of those by clearing them. If there's like terms that we can combine, so there's less terms involved, we're going to do that. Once we do that, the worst case scenario that we can be at is having an x and a constant on one side and an x and a constant on the other. And so the next step is to say, let's get all the x's to one side and all the non-x's, the constants, to the other. We're going to use addition or subtraction to do that. And now, worst case scenario, we have some x's on one side, numbers on the other. And so we can just divide by whatever coefficients in front of the x to get the x by itself. At which point we have x equals a number. And that's a solution to an equation then. So with that said, let's go ahead and look at an example of how this is going to play out. So to clean up this first example, we're going to have to get rid of some parentheses. We're going to have to distribute. So that's the first thing that we're going to do. Now I do want to remind you that that 2 in front of the first parentheses isn't really a 2. It's a negative 2. We got to remember that the sign is always attached to the number. So we're going to copy the 7x down, but we're going to distribute this negative 2 across. And then over here, we'll distribute the 5. All right, so still in the clean it up step now, we're going to combine some like terms. So we've got the 7x minus 6x is x. All right, so now we're done to clean it up. But then the next step is to bring all the x's to one side, non-x's to the other. So we could go ahead and add 10x to both sides. That will get all the x's to the left. That way we have 11x minus 2 equals 20. Then to get the non-x's to the other side, we can go ahead and add 2 to both sides. That's going to get us 11x equals 22. Then if we want to try to get the x by itself, we'll divide both sides by 11, getting us x equals 2 as a final answer. And it's always a good idea to check your answers when it comes to solving equations, and it's honestly pretty easy. All you got to do is plug that 2 back in the original equation and make sure it ends up being something that's true, making sure that when you plug 2 in for all your x's, you get something like 5 equals 5 or 10 equals 10, something that's true. And as long as that's the case, you know your answer is correct. Now in these next two examples, I'm not doing by hand, I'm not walking through all the steps because they're basically the same as the last one. But we start off with a linear equation. After going through all the steps to solve it and try to get the x by itself, you'll notice that something weird happened. You'll notice that we had 8x on this side and 8x on this side, so that when I subtract 8x from both sides, the x portion goes away. And we're just left with negative 8 equals negative 10. No x is involved at all. So what does this tell us about our solution? So we got to consider, what does this mean in terms of trying to solve this equation? Well, if we go back to what it means to be a solution, we want to remember that a solution is the value or values that make the equation true. Our equation is currently negative 8 equals negative 10. If x equals 5, does negative 8 equal negative 10? No, it doesn't. If x is 10, does negative 8 equal negative 10? No, negative 8 does not equal negative 10. Well, what if x is a billion, million, trillion, whatever? Does negative 8 equal negative 10? No. There's no value of x that you can pick that will make negative 8 and negative 10 the same thing. And therefore, that equation that we started with has no solution. It doesn't matter what x is. There's no value that will make that equation true. Now, the flip side of that coin is if we look at an example like this one here, that once we work everything out, similar happens that the x's go away, but we end up with negative 24 equals negative 24. If x is 7, does negative 24 equal negative 24? Yes, that's a true statement. So 7 must be a correct answer. If x is 10, does negative 24 equal negative 24? Well, yeah, so 10 must be an answer. Doesn't matter what x I pick, negative 24 does equal negative 24, meaning all real numbers work. There's an infinite number of solutions, and any real number would actually make that equation true. So all real numbers are a solution to that equation. So we talked about with linear equations in the clean it up step that if there's fractions involved, that we want to clear the fractions. A good general rule of thumb for our class is that we're going to say fractions suck. Get rid of the fractions. If we can avoid dealing with fractions to begin with, that's what we want to do. So here's an example of an equation that has fractions in it. I want to talk about how to do this, how to get rid of fractions. So let's first of all try to live in kind of a perfect world where we just want to do something mathematically that might not be legal. So to get rid of the fractions here, it would be nice if I could just multiply by 8 on that first fraction. That would allow me to get rid of the bottom, and it would be gone. If I could do similarly and multiply the second guy by 3, the fraction would be gone. And if I could just multiply this guy by 6, the fraction would be gone. Now, that's all well and good. It's totally illegal. We cannot do that. But the idea is there to say, well, it sure would be nice if I had 8 to get rid of the 8 there. I could legally do that if I also multiplied the other side of the equation by 8. That would work. And similarly then, putting that 3 in the middle would have worked if I would have multiplied both sides of the entire equation by 3. So what we'd like to do is to say, if I could multiply both sides of my equation by all the denominators, that would be great. But that might be a really big number, so we don't want something that big. We just want to make sure that an 8 is in that number, a 3 is in that number, and a 6 is in that number. By definition, that is your least common denominator. And so that's really what we want to do in order to clear fractions, is we want to multiply both sides by the least common denominator. That's how we can clear fractions. Let's go through with clearing the fractions. The least common denominator between 8, 3, and 6 is going to be 24. So we're going to multiply both sides of the equation by 24. Now notice that we're only doing this in the top because our goal is to get rid of the bottom. This is something that some people get confused on because there's times that we multiply by something on the top and bottom. So keep in mind what your goal is. Your goal is to get rid of the bottom, so we only want it in the top. So let's go ahead and distribute that 24. Before we divide anything out, let's just go ahead and put 24 into the top of the first fraction. Let's put 24 into the top of the second fraction. And let's put 24 into the top of the right-hand side. Then we can worry about the division part. So then we can say 24 divided by 8 is 3. 24 divided by 3 is 8. And 24 divided by 6 is 4. Now we have a linear equation that's set up a lot more like some that we already looked at, where we can just distribute, combine like terms, and solve. So let's go ahead and do that, and we'll go through a little bit quicker since we kind of know what we're doing now. But we're going to distribute each of those values, and 4 times 5 is 20. Then we'll combine some like terms. Then we can add the 13 to the other side. Then we can divide by 11, and we get a nice happy answer of x equals 3. So now we're going to talk about quadratic equations. Now, a quadratic equation is an equation with a degree of 2, meaning there's an x squared somewhere in the problem. So that's what we want to look at when it comes to a quadratic equation, is seeing that there's an x squared. Now, we're going to learn some really cool ways of solving quadratics a little later in the course, but in terms of review, the one thing that you've learned to solve quadratic equations in the past has been what's called the zero factor property. And the zero factor property is just a property about numbers that says if I'm multiplying two numbers together that equals 0, then one of the numbers better be 0. So in terms of solving quadratic equations, what we're going to do is we're going to factor. We're going to factor the quadratic until it's two things being multiplied together. And of those two things multiplied together that are equal to 0, one of them better be 0. And that's how we're going to solve a quadratic equation. And so again, when solving a quadratic equation, we first of all want to make sure it's equal 0, so we can use the zero factor property, which this one is, and then we're going to factor it. So we're going to try to say, how do I rewrite this as two parentheses, as two factors multiplied together that equals 0? So we have 3x and x to get 3x squared, but then we need to get negative 14 somehow. So we're going to go back to our old educated guess, check, and revise. And we're going to say, I need to make sure that I got a 7 somewhere and a 2 somewhere. And for my check part of guess, check, and revise, I have 6x minus 7x is negative x. That is my middle term. So this is the correct factorization. And now the zero factor property says I'm multiplying 3x minus 7 and x plus 2 together, and that equals 0, which means either the 3x minus 7 needs to be 0, or else the x plus 2 needs to be equal to 0. If the 3x minus 7 is equal to 0, then x must be 7/3. If x plus 2 is 0, then x must be negative 2. And so now in our homework, we can write this as 7/3 comma negative 2. It's just important that we don't put parentheses around there. This is not an ordered pair. We're not saying x is 7/3 and y is negative 2. We're just using a comma to separate the two values. And we will often get two answers for a quadratic equation because we can see there's these two different factors involved.